Okay, so glad to see some people are on. Um, let's see. I don't think I have any announcements for today. So we'll go ahead and dive in, and people who aren't here yet. Does anybody have any questions? All right, so that's 3 students. We have reached quorum. Get started. Um, so today I'm going to talk about another method of solving that we've been talking about. First order linear PEs. So, right, there's a first order part to this definition. Well, obviously we're talking about ODEs. And then there's this linear component, which all of these things put together meant that we could take the differential equation that we're dealing with and write it in the form y plus p of x, or sorry, y prime plus p of x y is equal to q of x, where this p of x and q of x are merely functions of x. So they don't depend on y. So we went through a method yesterday of solving equations like this by first solving the homogeneous version, which was a separable ODE, and then solving the non-homogeneous version if we needed to, if q of x was not equal to 0, so if we weren't dealing with ODE, linear ODE. And this was by variation of parameter. Question. Oops. Change the view. Okay, there we go. All right, so right, so that's how we do that yesterday, and we're going to look at a different method today. It's basically the same thing. We just kind of go through the steps in a different way. But before I do that, I'm going to talk about a very common type of word problem that people who teach this class very often like to use in order to illustrate the use of linear first order ODEs. And this is the sort of a tank filling up with a fluid. It has a certain concentration of something, blah, blah, blah. Okay, so we'll go through an example of that today because I know that there's one on the web. There might be one on the exam, not sure. Okay, so we're going to have a 100-liter tank. So I'm going to go through the illustration. Of course, when you solve a problem like this, it's not necessary to draw a picture. Sometimes it's helpful to think about it. So this tank is 100 liters total, and it has the water level, 60 liters of water, and 10 kilograms of salt are dissolved in it. So this is a saline solution of some concentration. Okay, so into this tank, we have flowing a solution That is, it's flowing in at 5 liters per minute, and it has a concentration of 0.1 kilograms of salt per liter of water. So we've got some more salt flowing in along with some water. And we also have a port down here at the bottom where liquid is flowing out, and it's flowing out at a rate of 3 liters per minute. And we make this assumption that the fluid in the tank thoroughly, probably write that correctly, thoroughly mixed. So everything has the same concentration. There's not more salt at the bottom, there's at the top or something like that. So the liquid that's flowing out, we assume that the concentration is just however much salt is in the total solution divided by how much water. Just to simplify the calculation. Simplify it to the point that we can actually solve it. Okay, so the question is there's a variety of things it could ask. Usually it's going to be asking how much salt is in the tank at time t, the final. Okay, so they might give you a certain final time and ask how much salt is in there. So how many kilograms of salt are dissolved in the water? They could also possibly ask what is the concentration at a particular time, or well, here's another example, slight variation in this problem. How much salt is in the tank when it is full? And this is something that we can figure out based on how much fluid is flowing in versus how much fluid is flowing out, and how much is in there initially. So we will take a stab at this problem. How do we set this up? So if we think of, oftentimes in textbooks they'll write this. Well, let's specify what our term is. So X is going to denote amount of salt in the tank. This is in kilograms. And then T is going to denote time elapsed. And that's going to be in minutes. Sorry, I got my COVID shot yesterday, so if I'm a little off today, that's the reason why. So that's what our terms are going to denote. And then oftentimes in a textbook, you'll see something like delta X is the change in a certain small amount of time. Okay, so we say that delta X is approximately equal to how much salt is flowing in this amount of time. So in the same small amount of time, we have 5 liters per minute flowing in and 0.1 kilograms per liter. So we have 0.5 liters per minute. I'm just going to leave units off. All the units kind of cancel out correctly, so I'm not going to. So 0.5 times the amount of time that passes, so that we write that as delta T. That's how much is flowing in, and so we'll subtract away the amount that's flowing out. And so that's 3 liters per minute. And then we're going to multiply this by the kilograms per liter. So in order to do that, we need to know how much kilograms there are per liter. So we'll take the number of kilograms total, that's X, and we'll divide it by the number of liters total. So the number of liters is going to start off 60. And then we're going to have 5 flowing in per minute. So that's 5 times how much time has elapsed total. And then minus 3 times, because 3 liters per minute are flowing out. So this is the total amount that's gone in so far, minus the total amount that's gone out so far. So that'll give us our concentration. So 3 liters per minute times a certain number of kilograms per liter. And then we multiply that by how much time has elapsed. No, I'm sorry, not how much time has elapsed. Our little measurement of time. So we're saying the amount of the tank is changing in this small amount of time, approximately equal to how much is flowing out in that small amount of time. Or sorry, how much is flowing in minus how much is flowing out in that small amount of time. And then in our calculus way of thinking about modern calculus way of thinking about things, we take the limit as this delta t goes towards 0, right? So this gives us an expression. We kind of mentally go through the steps of thinking about this in terms of limits and write it as dx dt equal to 0.5 minus 3 times xo. And then I'll just simplify our denominator, because 5t minus 2, or 5t minus 3 is just 2. Now, the point of view that the way that I'm thinking about this thing, and like I've said many times, the way that people early in the history of calculus were thinking about these things, they weren't thinking in terms of limits and doing this kind of argument of what is the definition of dx dt. They were really thinking of these things as numbers. And so when delta x got arbitrarily small, they would think arbitrarily small but not 0. It would be a number, and they would call that dx. Of course, the delta is the Greek letter for d, so you see the connection. And they thought of this as, these are just, in our limit way of thinking, we think as it gets smaller and smaller, the approximation gets better and better. In the ancient way of calculus thinking, they thought of these things as being concepts that made sense. dx is just an infinitely small amount of salt. dt is an infinitely small amount of time, infinitely small, but not 0. And so when we divide both sides by dt, it makes sense. We're not dividing by 0. So that's we're not supposed to talk in these terms in a calculus, undergraduate calculus, or in a graduate. But I'm going to pull back the curve a bit. Since time has passed, mathematicians thought about this problem for a while, and they've found ways to make all of this reasoning logically rigorous. Unfortunately, it involves expanding our number system beyond something which is often referred to as the hyperreal. But put that aside, and just we'll continue to think in the way that Newton and Leibniz thought about calculus. Just a way of simplifying things. So anyway, we've got our dx dt, which we also can think of for x prime. And when we write this as a first order linear ODE, we get x prime plus, factoring all this stuff out that's multiplied by x, we get 3 over 60 plus 2t times x equals half. Okay. Now, we think of or we denote this thing by p of x. So little p of x, I will write as 3 over 60 plus 2t. And then we take its antiderivative. So e to the negative of the antiderivative of this thing gives us our homogeneous solution. So let me just write it like this because it's going to simplify, fortunately. So I'm writing this x star to be our homogeneous solution. That's the solution that we get if we ignore this 0.5 part. So if that was just a 0, we would go through this as a separable ODE, and we would come to the solution. Anyway, the solution is going to be e to the integral of minus p of x dx. So the integral of p of x, let me write this in a simpler way, minus integral p of x dx. I'm going to use capital P of x to denote some antiderivative, little p of x. So the antiderivative of this is I want to write this out just so you can see the steps I'm going. I'll pull out the 3. That's not going to be great. And I will write this as 1 over 60 plus 2t dt, leaving a little space in front of dt. So I can do u substitution. You remember from way back in the day. So this on the inside the integrand, or integrand here, that's going to be, we're going to get the natural log of that thing in the denominator. But we need to be able to say that we have the derivative of the denominator somewhere on the outside for our u substitution. So the derivative of the denominator, it's just a linear function, 60 plus 2t. That's just a function of a straight line. The derivative of that is 2 dt. And so I need a 2 times my dt, and I will compensate for that by dividing by 2 out in front. And when I integrate this, I get 3 halves natural log the absolute value of 60 plus 2t. And because we only care about one particular constant of integration, or one particular antiderivative, we'll just choose the one without the constant. Because like we said yesterday, it ends up just going away in the process. So we don't end up using it. Okay. So when I put this into my homogeneous what was I saying? Let me just check my notes to make sure I screwed anything up at this point. Nope, still good. So when I put this into here, I get e to the 3 halves natural log of the absolute value of 60 plus 2t. Oh, at this point, we can go ahead and say what our stationary solution is. So our stationary solution is going to be, all right, screwed that up. So our stationary solution is going to be what we get whenever we have p of x is equal to 0, little p of x. Or we should say when it's discontinuous. Also, when we get it's discontinuous when t is equal to minus 30. And of course, this is backwards in time. So we're only thinking about moving forward. T is equal to, we'll just ignore this part. So we can assume that t is positive and we don't need this absolute value anymore. And so I'll just write this as natural log of 60 plus t. Just a little bit of justification for dropping that absolute value. Okay, so of course, by rules of exponentiation and natural logs, so forth and so on, what we get is that this is equal to 60 plus 2t to the 3 halves. Sorry, to the minus 3 halves, because forgot about my mind. Okay, so that's our homogeneous solution. And now we get our non-homogeneous solution as x of t is equal to some u of t times x. Oops, didn't mean to do that. That looks kind of cool. Maybe I should just stick with it. X star of t. So when we did our homogeneous solution, we would have ended up with a constant here. So yeah, it's a good time. Green. So we would have had some constant out here that came from our constant of integration, right? And what we're doing in our variation of parameters is we're replacing this constant with some function and seeing if we put some function in there instead of the constant, can we retrieve our non-homogeneous solution based on that? So that's what we're going to do. We're going to say u of t is some function. And so whenever we do this, what we found was that u of t, plugging this back into our linear first order of t, working through the steps, blah, 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 we get that u of t is equal to the antiderivative of q of t divided by x star. So we took our non-homogeneous part, which was this 0.5, and we divide it by our homogeneous solution, which is this. Then we took its antiderivative, and we got this. And so what does this end up being? Well, our q of t is just 1/2. So I'll just pull that out in front. And 1 over our homogeneous solution, x star, is just, what did we get? This was 60 plus 2t to the minus 3/2. So the reciprocal of that is just 3/2 dt. A little room again. Because I'm going to do u substitution again. Basically, I just need something. I just need a 2 dt to account for the derivative of this thing. Where u substitution is just chain rule in reverse. So to compensate for that 2, I need to divide this thing by 2, so I'll get 1/4. Everything balances out. And then I do my antiderivative, and what I get is 1/4. 60 plus 2t going up by 1 gives me 5/2. So 3/2 plus 2/2. And then I divide by my new exponents, so that's 2/5 plus c, and of course this is equal to 1/10 times 60 plus 2t to the 5/2 plus some constant. Okay. Now, almost finished. We get our we put these pieces all together to get our solution to the ODE, not our solution to the question. So our solution to the ODE is going to be, this is our u of t times our x star. So what I get is 1/10, and then I've got this factor times this factor. So it's that thing to the 5/2 times that thing to the 3/2. 5 minus 3 is 2, so those cancel out. Get 60 plus 2t to the 2/2. It's just 1. Okay. And then plus our constant of integration times 60 plus 2t. You see our homogeneous solution always ends up appearing as a piece of this. Then we've got this is our homogeneous part of the solution, right? That's just, right, that's the 5/2. Our homogeneous part. So our homogeneous part always appears in the solution, and then there's something added to it that corresponds to our non-homogeneous part. Now, what we can do is we can plug in our initial condition. So we had t equals 0 gives us, well, let me just write it, x of 0. So this is, when we have t is equal to 0, we get 6 with our first term, and then plus c times 60 to the 3 halves. And unfortunately, I don't think I wrote down what this works out to be. We get that this is equal to 60, because that's our initial volume of the tank. I took this from the book, so maybe I can just look in the book and see what this works out, or what we end up getting for C. In any case, you would simply just plug this into your calculator. This is not something I'm interested in working out. What did they get for this? They got that C is equal to approximately 1859.03. It doesn't work out to be anything, so we just plug it into it. Okay, so now we go back and try to figure out, so that the question was asking, well, we plug this in here for C, and we get the amount of salt in the tank at any time, but we want to know the amount of the salt in the tank when the tank is full. So we need to figure out what time that happens, and we know how the volume of the tank is changing. It's just 60 plus 2t, right? That's what we worked out at the beginning. Let's see, when we were looking right here, this was the, get a highlighter. Very good. That's the volume of the water for the saline solution. I'm trying to, there we go. So this is the volume, and we want to know when it reaches the total volume of the tank, 100. And so, of course, for this, we just get T is equal to 20. And so we plug in 20 into our equation, and we get, so I'll tell you what it is, 11.86. So, or I should say approximately. So this is how we work through one of these tank problems. And there are a lot of variations on this. You know, there's that sort of skill of noticing that the word problem is exactly the same as the word problem we've seen before. It's just got the terms changed. Anyway, maybe I should call this E sub 4. Okay, are there any questions about these kind of tank problems? There was an initial step that we did of taking it and turning it into a first order linear ODE. And then once we were at that point, we kind of forgot about what the word problem was saying about real world stuff like water and salt, and just did a math problem. And then at the end, we did maybe a little thing saying what we're actually talking about is salt. So this is how much salt we have. Okay, if there are no questions, I'll continue. With what I said, what we were talking about today, and this is a sentence that I actually say an English sentence there. What we were originally going to be talking about today which is this other method of solving first order linear ODEs, just basically the same. It's just does the steps in a different order and has a different name. And so I'll just expose you to that for the sake of knowing what it is. Okay, so let's go back to our general form of a first order linear ODE, which is this. And the basis for this method is noticing that this part of the ODE right here, it looks a lot like what you would get if you were applying the product rule to some function times y. So if we were taking the derivative of this thing, we would get r prime of x, y of x, plus r of x, y prime of x. And so we already see our y of x and our y prime of x, and we've got some function multiplied by it. And so what we're looking for is some factor that we can multiply through this equation by, so that we get something that we can rewrite as the product rule. We rewrite it like this. Because once we can rewrite it as just the derivative of something, we just integrate and we've got, we take the antiderivative and the derivative goes away. So the trick is figuring out how this works. So we're going to go ahead and just say this r of x is the function that we're trying to find. We're going to multiply it by this y prime anyway. So we multiply through by r of x, and I'll get r of x y prime plus r of x p of x y is equal to r of x q of x, right? And so now if this is what we're looking for here and here in the reverse order, this is the first one, right? Then the first term looks fine. The second term is what we have to figure out. So that's telling us that this part right here is equal to this r prime. So what we get is that r prime, myself a little room, r prime of x is equal to r of x p of x. And if we write capital P of x is equal to the antiderivative P of x, then we have a really obvious candidate for r of x, and that is r of x is equal to e to capital P of x, which is almost exactly what we had for our homogeneous solution before, right? Okay, foreshadowing. So that allows us to rewrite this side as the integral of r of x, or sorry, the derivative of r of x, y of x equals r of x, q of x, right? Now we just integrate both sides. This gives us r of x, y of x is equal to the integral of r of x, q of x, dx. Okay. So we know what r of x is. We multiply it by q of x, integrate, and then we divide by r of x here. And so what we get at the end is y of x equal to dividing by r of x, integral of r of x dx. And if we want to not forget about our constant integration, write it in. But of course, that's implicit in our antiderivative. That makes sense. Now let's go back and see that this r of x, remember, this is just e to the capital P of x. Our original method of solving this was getting the homogeneous part, the solution to the homogeneous version. So this is y of x. This was just equal to e to the minus capital P of x, just the negative of the derivative. So what we have is that r of x is really just equal to 1 over y star of x, right? So if we go back and look at this thing, what we get is just y star of x times the integral of u of x for y star of x dx. This was just y star times u. That was the that we were. So you see it works out to be the exact same. Some people find it easier to think about things in terms of the homogeneous and non-homogeneous parts. Some people find it easier to think about the problems in terms of what this thing here is called. So this method is called finding an integrating factor, or method of integrating factor, or integrating factors. So when you see something saying use integrating factors, or the integrating factor is blah blah blah, or things, then you'll know what it means. It's just the reciprocal of the homogeneous solution. Okay. Now, if there are any questions, speak now or speak later. But if there are no questions, I'm going to go on to some examples. Okay. So let's do a first example right here. And this is y prime plus, we'll start with something relatively simple, which is this. So what we have here is p of x is equal to x, q of x is equal to x. And I think at this point, oh, you know what? Save it for next. I'm gonna let you try this one for a minute, and if anybody comes up with a solution, let me know, and we'll work through this. Well, let's work through it separately. We'll come together. You might feel like they have a certain point. It's probably a little bit late in the class to say this, but I just want to remind everyone why you come to Zoom. Okay, I'm going to go ahead and try to work through this, and there's a couple more problems. I want to get to a couple of more examples today. Um, I'll go ahead and give this one a shot. The first thing I want to point out is that P of x and Q of x are actually exactly the same. So that fact will come back to be interesting in just a minute. But let's do this using the method of integrating factors. So the antiderivative of x is x squared over 2. And so our integrating factor is just going to be e to the x squared over 2. So I can rewrite this thing as e to the x squared over 2 times y. Derivative of that thing, that product, is equal to e to the x squared over 2 times x. So actually, this looks fairly promising. If I take the integral of both sides, the left-hand side by the fundamental theorem of calculus, just e to the x squared over 2 times y, plus some integrating constant that we're going to fold into the other side. And on the right-hand side, we have e to the power of something, and then the derivative of that something is just there multiplied by it. So we've already got our u substitution nice handled for us. And so what we get from this is on this left-hand side, the x squared over 2 plus some constant differential. So that works out really nicely, and we can solve for this. Okay. Sorry, I got distracted by my own notes. So we just divide on both sides by e to the x squared over 2, and we get y is equal to e to the x squared over 2 divided by e to the x squared over 2 is just 1. So we get 1 plus c times e to the minus x squared over 2 because we're dividing. All right, next. Oh, an interesting thing to note. We had here a stationary solution of y was equal to all right, let me just ignore that. Stationary solution, that's for the separable part. Okay, so I'll actually come to that right now. One thing to note about this this linear first order ODE, which we can solve by using integrating factors, is that this is actually just a separable ODE. And that happens a lot. If we have y prime plus our p of x times y equals q of x. And our p of x is actually just a constant multiple of our q. So we can write it like this. And we can rewrite this thing as y prime is equal to q minus a q y. And we can factor out q of x. And we get that 1 minus ky, right? So this is a function just in terms of x. This is a function just in terms of y. So we could have solved this just using separable equation or separable ODE. I'm going to do that really quickly just to confirm that we get the same answer. We have y prime, which I'll write as dy dx for the sake of easy separable equation solving. And what I get is, if I subtract this over to the other side, I get x minus xy, which is equal to x times 1 minus y. And I can rewrite this as dy over 1 minus y is equal to x dx, integrating both sides. Over here, I get the natural log the absolute value of 1 minus y. And on this side, I get x squared over 2. And I'll go ahead and include the constant there. Now, I should have looked at my stationary solution. Of course, it comes from right here. That's y is equal to 1. So we're going to assume that y never passes through 1, except at our stationary solution. And so we either have y is always above 1 or y is always below 1. And so, in the end, we're going to end up with this constant multiplied by an exponential. So that permits me to just ignore this absolute value. And so I'm just going to have natural log of 1 minus y is equal to, actually, let's go through the steps of showing why I can ignore it. I'm going to exponentiate both sides and get absolute value. So y is equal to c e to the x squared over 2. Remember that e to the c, I'm just going to rewrite as a constant in front. And then, like I said, we're always going to be either in the positive regime where we're above 1 minus y, or we're going to be in the negative, above y equals 1 or below y equals 1. So if we are in the above y equals 1 part, then this thing right here will be negative, and we would need the absolute value to give us a positive thing. So we just make c negative. And if we're in the y is below y equals 1, then we'll be in the part here where the absolute value doesn't matter. We can make c positive. So that allows us to it allows us to completely ignore the absolute value. I made a mistake. I'm sorry. It's a small mistake, but it is in our u substitution, and I've done it already twice today, and so I should have noticed this. But we need dy to be negative, right? In order to do u substitution, because the derivative of 1 minus y is negative 1, I needed a negative dy. So I'll make this whole thing negative in order to cancel that out. So what I should have got here is negative natural log. And when I move that over to the other side, I get e to the minus x squared over 2. And so now I add my 1. Oh, all right, no problem. I add my y to the other side, and I subtract this from the other side, and I get y is equal to 1 minus ce to the minus x squared over 2. And you'll notice here I got a plus ce to the ce to the negative x squared over 2. That's no problem. I'll just flip the sign on c again to make it positive. I'll just flip this sign on and make this thing positive. C is an arbitrary constant, so we can do things like that without any justification. Okay, and you see we get the same solution. This often happens because, well, this is a challenge for the person who's coming up with problems. They have to come up with problems so that when you do these integrals, you end up with something reasonable. And that's kind of difficult to do, just random P's and Q's. And so they have to be kind of careful. One of the ways to be careful is to just say that um, P is some constant multiple of Q. And then, you get a nice integral. The problem is that if you're using these for examples of linear ODEs, you want to force people to use integrating factors. Well, they could have done this with a separable equation, but it's not really working. So let's move on to one that's not separable. Actually, two that aren't separable. If we have time. And here's the thing. I don't take attendance. I already made the point that someone doesn't have their camera on. They are not allowed. So I'm sticking someone in a waiting room. Okay. So, and they can email me. They saw most. Okay. So let's go through an example here. Oh, what I was going to say is, I don't take attendance anyway, so you're always, I'm going to continue. We might go over at the end of class, and you're free to leave at the end of class, but of course you're free to leave at absolutely any time you want to. Okay, so here is a problem. I think, if I'm not mistaken, Sydney, this is one of the ones I'm going to look at. Okay, so let's try this out. We'll do it in a different color. So let's do this one in blue. So y prime minus 2t y is equal to 9t squared e to the t squared. This is another trick of people who have to come up with these kind of problems, is that you stick an e to the something over here and everything. Okay, so method of integrating factors. We'll do that this time. So the integrating factor is going to be e to the minus t squared. So I'll go ahead and just go. Actually, let's do the steps. Minus 2t, this goes to t minus t squared. And so this gives us our integrating factor, e to the minus t squared. So if I multiply through by that, I get e to the minus t squared y prime, rewriting this thing as using the product rule. And on this side, I just get 9t squared, because that e to the minus t squared cancels out with the t squared. So I'll take the antiderivative of both sides. I get e to the minus t squared y is equal to, this one is easy. I don't think I have to write this one down. 3t cubed plus c. And so what I get at the end is y is equal to 3t cubed e to the t squared plus c e to the t squared. Should have left this as an example for everyone. Oh, there was an initial condition on this too. Well, that's okay. Y of 0 is equal to 4 was our initial condition. So if I plug that in, this part becomes 0. T is equal to 0 makes this part 0, makes this part 1. And so we just get C is equal to 4. So 3 cubed squared plus 4e t squared. Would anyone like to see this worked out as the homogeneous and non-homogeneous parts? I'll just say really quickly that the homogeneous version of this is y prime t y is equal to 0, right? We drop the non-homogeneous term over here. And so if we were solving this, what we would get is dy over dy over y, and then equal to the integral to t. And of course, this gives us e to the t squared. So that would be our y star, which is, of course, the reciprocal of our integral. This is an easy way to kind of check that you're getting the same thing. And then u of t divided by y star of t, which is 9t squared. And so integrating both of these, we get that 3t cubed plus c. Now, as we saw, c is 4. So when you multiply this by this, or u of t, that's our version from the non-homogeneous way of doing this. Then you see that you get ut times y star. You get the same. I went through that one kind of quickly. Do I need to leave this on the screen? Is everybody good? Anybody want me to leave it? Also going to be on YouTube. Uh, don't forget to like, share, and subscribe. You don't actually have to do it. Okay, so the next one. So this was an example of one that wasn't separable, which is kind of a difficult thing to do. This one, interestingly, does not use that factor of e to the something in order to cancel out. So this turns out to be an interesting one. This is not separable, and it's not set up like the other one. So I'll give you a chance to try this. You probably already have it work. Anyway, give this one a shot. Anyone want more time to raise your hand? Okay. Well, in that case, I'll give it a shot myself. So if we rewrite this, actually, just looking at this, you might be tempted. I was tempted anyway to try to figure out if there was something that I could go at this from the other direction. There's something I could multiply through so that I could get something there, multiply by that y, instead of doing it the way that we've been doing it so far. It turned out to be easier, at least for me, to do it the way we had been doing it. And so that would be to get it into the standard form. That's y prime plus 1 over 3t y equal to 1/3 t squared. So in this case, we get that our p of x is equal to 1 over 3t. And so that means our capital P of x, the antiderivative of this thing, is, checking my notes here, 1/3 natural log of the absolute value of t. Now, if I look back here at my P of x, I see that there's a discontinuity at t is equal to 0, which means that if we have a solution to this, it's only going to extend along the positive part of the x-axis, or sorry, in this case, I made that mistake earlier and I made it again. This should be P of t, capital P of t. So it's only going to extend on the positive part of the t-axis or the negative part of the t-axis. So there's not going to be any solution that we have that includes t is equal to 0 because of our existence and uniqueness theorem. So this discontinuity violates it there. So we only have from negative infinity to 0 at best, or from 0 to infinity at best. So because of that, we're going to assume that, we'll come to that in just a second. So when we look at our r of x, this is going to be equal to e to the 1/3 times the natural log of the absolute value of x. And we're just going to account for that absolute value by saying, well, let's just assume that t is positive. We can get rid of that absolute value because we're just going to look in this region right here. I can't remember if the problem says that we should do that or not. But anyway, that gives us our justification for ignoring the absolute value and using our laws, exponentials and logarithms. We get that this is t to the 1/3. So what we get here is that t to the 1/3 y is equal to the integral of 1/3. Now we have t squared times t to the 1/3. 2 is 6/3. So we get an additional 1/3, that's 7/3 dt. Now this is a not so bad antiderivative to get. The t will go, well, first of all, write down my 1/3 so I don't forget it. The exponent goes from 7/3 to 10/3. So 1 is 3/3. And then I get 3/10 multiplied out here, plus some constant. 3's cancel out. Okay. So now I need to divide both sides by t to the 3rd. I get y equals t to the 10/3 minus 1/3 is, write the 1/10 before I forget. T to the 10/3 divided by t to the 1/3 is t to the 9/3. 9/3 is just 3, so it's 2 to the 3. And then I'll write t to the negative 1/3, otherwise known as the cube root. Okay, that's it. So at this point, I will say thank you for coming. Good to see everyone. Have a good day, and I'll stick around if you have any questions.